Всем снова привет! Мы продолжаем нашу конференцию Upfest, и следующий спикер Лукас. Лукас, привет!
Hi everyone, we're continuing our... Yes, can you hear me, Lukas?
I can hear you, yeah, now I can hear you.
Excellent, excellent. We're continuing our conference. Lukas is here with us. Hi, Lukas.
Лукас, можешь рассказать, пожалуйста, пару слов о себе в начале?
Lukas, could you please say a couple of words about yourself in the beginning?
Yeah, of course. So my name is Lukas Lechner, and I nowadays call myself a freelance Android developer and online instructor. So this means that I'm not only working for client projects as a freelancer, but I'm also creating educational online content. And my last big project was an online course about Kotlin Coroutines on Android. And yeah, I'm based in Austria. And yeah, welcome to everybody.
Правильно я понимаю, что сегодня в своем докладе ты хочешь...
Am I getting it right that today in your speech you want to speak about Kotlin development, especially in the new version Kotlin 1.4? Is this correct?
Actually, I'm speaking about exception handling in Kotlin Coroutines.
Хорошо. Ладно, тогда не буду задерживать и...
Well, excellent. I won't entertain you any longer, and I'm giving the floor to you then. You have the words.
Perfect. Yeah, cool. So, perfect. So, let's start this presentation. So, welcome again, everybody from my side, and thank you for participating in my talk. And before I start, I also want to say thank you to the organizers of EppsFest for inviting me. So my talk is about why exception handling in Kotlin Coroutines is hard and how to master it. I actually had a slide about myself, but I already introduced myself, so let's skip this one and let's jump right into the subject. So the main benefit of Kotlin Coroutines is that we actually can write asynchronous and concurrent code in a sequential fashion by using conventional code constructs. So when you take a look at coroutine-based code, then this code will look pretty familiar to you because it's like written in a sequential fashion with conventional coding constructs. And even if you don't know a lot about coroutines, you will roughly understand what the code is doing. So Kotlin Coroutines try to be very intuitive. However, so this is mostly true, I think. However, there is one part that is not that intuitive, in my opinion, and you probably already guessed it. This is exception handling in coroutines. But first, before we talk about exception handling in coroutines, let's talk about exceptions in general. If we have some main function and some code that throws an exception, and we run this application, then of course this application will crash and exception thread main will be printed out. So this is a JVM main function, and all of my examples will actually be JVM main functions. However, on Android, there's pretty much the same behavior. The app crashes and Logcat will print out the exception. What can we do against this? Of course, we can use the conventional try-catch construct, and we have the code that throws the exception in the try block. And whenever this exception is thrown, we're able to handle the exception in the catch block. So when we run this program, handle exception is printed out. If that exception is not thrown directly, but in a regular function that we call, then the exception gets rethrown. And therefore, we are able to use a try-catch on the call side to handle the exception. So exception handling in general code is pretty straightforward. At some point, an exception is thrown, and then the exception is thrown up the call stack until it's handled at some point with try-catch construct. But if it's never handled, then the app will basically crash. Exception handling is much more interesting when exceptions are thrown in coroutines. So when we look at this example in which we have a root scope, which is basically a coroutine scope, and we launch a new coroutine in this scope, and this coroutine then throws an exception. And if we just run this app, then the app crashes and exception in thread default dispatch worker is printed out. And this is pretty much what we expect, because an exception gets thrown, but it's not handled at some point, so the app crashes. What we can do here again is we can simply use a try catch in our coroutine directly to handle the exception. So with the try catch, we are then able to handle the exception. If the exception is not thrown directly in the coroutine itself, but in a suspend function, then like a regular function, the suspend function rethrows the exception, and therefore again, we can use try catch on the call side to handle the exception. So exception handling looks pretty simple with coroutines, right? So why am I actually talking 30 minutes about it? Well, it gets much more interesting when we now put the exception back into the coroutine itself. And in the try block, let's start another coroutine. And in this coroutine, we throw a new exception. And I give you a couple of seconds, and you can think about what you think will happen when we run this example. So let's see what happens. If we actually run this app, then we are not able to handle the exception, but instead the app will crash and the exception will be printed out. And this is pretty confusing for lots of developers, because coroutines really promise us that we are able to use conventional coding constructs like a try catch here to write asynchronous code. And here you can clearly see that we're throwing an exception inside the try block, but for some reason we're not able to handle it in the catch block. And this is confusing and not that intuitive. But what actually happens here? In order to understand what happens, it's useful to have a look at the job hierarchy. So as you probably know, Kotlin Coroutines have this new innovative feature, which is called structured concurrency, which allows us to write our asynchronous code in a much safer way. And for some of the mechanisms of structured concurrency to work, the jobs of the coroutines that we launch actually form a hierarchy of their job objects. So for this code example, the job hierarchy looks like this. At the top, we have the job of the root scope. When we launch a new coroutine, this job now becomes the child job of the root scope. And when we launch another child coroutine, then this job becomes another child. And now when we throw an exception in this child coroutine, then the coroutine does not rethrow the exception, like for instance a regular function or a suspend function. Instead, the coroutine completes exceptionally, and when this happens, then the exception is not rethrown, but instead it is propagated up the job hierarchy. So at first it is propagated up to the parent of the child job, and this leads to a failure of the parent. And in turn, this exception is then also propagated up to its parent itself, the job of the root scope, and afterwards the exception is passed to the thread's CancellationExceptionHandler, and this means that our app crashes. So the reason why we're not able to use a try catch here to handle our exception is that a coroutine that doesn't handle the exception by itself does not rethrow the exception like a regular function, but instead it propagates the exception up the job hierarchy. So what can we do against this? So how can we avoid our app from failing in this situation? Well, we can install a coroutine exception handler. But how can we actually achieve this? How can we install one? As you might know, every coroutine and every CoroutineScope has a coroutine context. And in this context, we have some context elements which add some additional technical information to our coroutine or our CoroutineScope. And some of the context elements are the dispatcher, the coroutine job, the coroutine name, but also the coroutine exception handler. So the answer to the question of how do we install a coroutine exception handler is we simply add it as a context element to the coroutine context of either a coroutine or the CoroutineScope. This is how it looks in code. So we can create a coroutine exception handler by simply calling the coroutine exception handler function. And this function expects two parameters, the coroutine context, which is the context of the coroutine that has this coroutine exception handler installed, and the exception itself. And then in the body, we can basically handle the exception. And in our examples, we simply print out that we handled the exception in the coroutine exception handler. Now let's go back to our example that we had before. And as you can see at the top, I now created a new coroutine exception handler. And now we could install it in a coroutine, right? And we have several coroutines, and well, the child coroutine is actually the one that fails. So we can simply install it there, right? We can simply pass it to the launch coroutine builder, as you can see in the code, because every coroutine builder, we can pass some context elements to every coroutine builder. Therefore, we can simply pass the coroutine exception handler. But unfortunately, if we run this application, our app is still crashing. And that's also a bit confusing. But why is that? Well, as I said before, when we're not handling the exception directly in the coroutine, the exception is propagated up the job hierarchy. And this means that also exception handling is delegated to the root, to the parent coroutine. And since the coroutine has no coroutine exception handler installed, again, the thread's uncalled exception handler is called, and therefore the app crashes. So the solution for this problem would be to not install it in a child coroutine, but in the root coroutine. And if we do this, then when the exception is thrown in the child coroutine, it again propagates up to the root coroutine, and then it can be handled by the coroutine exception handler. The third possibility would be to simply install it in the root scope. So as you can see here, when we create a CoroutineScope, we can use the plus modifier to define more context elements. And now when we launch more coroutines, then these coroutines inherit the context elements of the scope. And therefore, the root coroutine also inherits the coroutine exception handler. And therefore, if you run this app, it also works. As you can see, root coroutines have some special properties. And the first special property that we saw was that we're able to install coroutine exception handlers in them that are actually called. All right, now you know basically the two options that we have for handling exceptions in coroutine-based code. The first one is to install a coroutine exception handler, and the other one is to use try-catch directly in the coroutine. But the question now is, in which situations should we use which of those two? So when you read the documentation of the coroutine exception handler, you will read that it should be used as a last resort mechanism for global catch-all behavior. And catch-all behavior means that that the coroutine exception handler will be called whenever a child coroutine throws an exception. The problem though is that when we get an exception in the coroutine exception handler, then the coroutine that had thrown the exception has already completed, and therefore we are not able to recover from this exception. Some examples for using the coroutine exception handler would be to log the exception, for example, to a crash reporting system, or to show an error message to the users. What you should not do is to simply install an empty coroutine exception handler just to avoid crashes in your application, because this is like an empty catch block, and this way some severe issues in your application could stay unnoticed for a long time. With try catch, on the other hand, we are able to handle the exception directly in the coroutine itself. And this means that we have the possibility to recover from the exception. Some examples for using try catch in the coroutine directly would be to retry the operation. So for example, when a network request in the coroutine fails, we could retry it, but we could also perform other arbitrary operations. For instance, when the network request fails, we could instead load the data from the database. However, when you use try catch, there are two very important aspects you need to consider. And the first one is you always need to keep the cancellation mechanism of structured concurrency in mind. So what do I mean by that? Let's take a look at another code example in which we have a root scope in which we launch a new root coroutine. And in this root coroutine, we launch two async child coroutines, and each of these child coroutines performs a network request. We store the result of this network request in its own variable, and then we display the result of both network requests to the user. What's important to mention here is that we only want to show something to the user in case when both network requests are actually successful. So we don't show like partial data when only one of these two network requests is successful. And the code, as we have it here, is correct. Because when we run it, so at first let's take a look at the job hierarchy. We have the job of the root scope. We have the launch coroutine, that's the root coroutine, and we have the two async child coroutine. And now when we run the app and when network request 1 fails, then this first async child coroutine completes exceptionally immediately, and therefore the exception bubbles up to the parent, the root coroutine that was started with launch. This means that this root coroutine also fails, and this means that it cancels itself and also the other async coroutine. So in this case, as soon as one network request fails, the other one is also cancelled and the user sees the error message immediately. And we are also not wasting device resources because the other coroutine is cancelled immediately. So this code works properly. However, then the project manager comes and says, well, I think network request 1 fails quite a lot, so could we maybe log this with our crash reporting system because we want to investigate it in the future? And we as developers say, of course, yes. And what's our first intuition is, well, simply use a try catch in the first async coroutine and surround the network request in the try block, and then catch all exceptions and log the exception there to our crash reporting system. However, by doing this, we introduced a problem, because now when the first network request fails, the exception is handled directly in the coroutine itself. So the coroutine, the async child coroutine, doesn't complete exceptionally. And this means that no exception is propagated upwards and the second network request continues to run. And this is wasting device resources, and also the user needs to wait longer to see his error message. What can we do to fix this? Well, try catch is not correct here. Instead, we should use a CoroutineExceptionHandler and install it either in the root scope or in the root coroutine as we do it here. The second really important aspect when you use try catch is that you might catch a cancellation exception, and therefore your coroutine continues to run. I want to explain this also with a code example. So here you can see that we launch a new coroutine and we store the job of the coroutine in its own object. And in the coroutine, we basically start a new network request, and then we delay for 1000 milliseconds in order to simulate the network request. And then we print out that the coroutine is still running. Below the coroutine, we delay for 500 milliseconds, and then we cancel the coroutine. So here we are basically just canceling the network request while it is still in flight. And when we run this app, at first starting network request will be printed out, and then after 500 milliseconds, the delay suspend function will throw a cancellation exception after 500 milliseconds, and therefore this coroutine will complete exceptionally with the cancellation exception, and the coroutine stops its execution. So this code is actually correct. However, again, the project manager comes in and says that, well, the network request seems to fail quite often. Can you please again log it to a crash reporting system? And we, of course, again say yes. And the first intuition would be to, again, use try catch. And yeah, we're basically doing the network request again in the try block. And then in the catch block, we log the exception to the crash reporting tool. However, again, we introduced a problem here, because when we now run this app, then again, at first, starting network request is printed out, and then the network request will be executed. And after 500 milliseconds, the cancellation exception will actually be thrown in the delay function. However, since we handle the exception, since we catch all exceptions and we handle it directly in the coroutine doesn't complete exceptionally. But instead, the coroutine keeps on running. So coroutine still running will be printed out. So again, we introduced a problem here by adding a try catch in our coroutine. So the solution here would be to not catch all exceptions, but only catch HTTP exceptions. Another possibility would be to rethrow basically cancellation exceptions in our catch block. And this way the coroutine also completes exceptionally, and therefore it stops its execution. There's this run catching function in the Kotlin standard library, which a lot of people like. But however, you have to be also careful when you use that regarding cancellation exceptions. So if you don't know run catching, this is how it looks like. The idea basically behind run catching is that you can pass a lambda to it, and then whenever this lambda throws an exception, run catching returns a failure result, otherwise a success result. However, when you use this function and your lambda is throwing a cancellation exception because your coroutine is cancelled, then the coroutine continues to run. There's also already a ticket in the Kotlin library on GitHub where a user wants to have a run catching version that is rethrowing the cancellation exception to avoid this problem. But up until now, we don't have this run catching method. So if you want to use your run catching in coroutine-based code, you should write your own run catching function, which looks like this. And the difference here is that we simply rethrow cancellation exceptions. And therefore, we fix this issue. Let's move on to take a look at exception handling for coroutines that are started with launch and coroutines that are started with async. Up until now, we only used launch to create root coroutines. And as a reminder, what happened when these coroutines completed exceptionally was that the exception is propagated to the parent, the root scope. And when a CoroutineExceptionHandler was installed, the exception was passed to the CoroutineExceptionHandler. Now, when we not use launch to start a root coroutine, but async, and then we throw an exception directly in the coroutine and we run this program, then actually there's no output. And this is interesting, right? So what actually happens here? Well, when we use async to start the root coroutine, then the exception also propagates up the job hierarchy. But even if we have a CoroutineExceptionHandler installed, the exception will not be passed to it. Instead, it will be passed to its deferred object. So, as you probably know, the coroutine builder launch returns a job of the coroutine. Async, on the other hand, returns a deferred, which is a special kind of job with a result value. And for async coroutines, the exception is encapsulated in this deferred object and will be rethrown when we later call await on it. So let's now create await on it, but first store the deferred in its own variable and then call await on it. But since await is a suspend function, we have to first launch a new coroutine in order to be able to call it. And in order to handle the exception that await is throwing, we can either use try catch, or we could also install a CoroutineExceptionHandler. It's a bit more interesting when we have not async root coroutines, but async child coroutines. So when we take a look, for instance, at this example in which we use launch to start a root coroutine and then use async to start a child coroutine, and now we throw again directly exception in the async coroutine. And if we run this app again, then on the right you can see the job hierarchy. And if we execute this app, then now it crashes. And this is interesting because before async was a root coroutine and there it did not crash, but now it's a child coroutine and now it crashes. So what happens here? Well, the exception leads to the async coroutine to complete exceptionally. This means that the exception propagates up to the launch root coroutine and up to the root scope. And since there's no CoroutineExceptionHandler installed anywhere, the app will crash. So that's interesting because we haven't even called await on the deferred object, but our app still crashes. So let's move on to some scoping functions. And let's take a look at the coroutineScope first. As you can remember, this is the example at the very beginning of my talk, in which we had a try catch in the coroutine, and in the try block, we launched another coroutine that throws an exception. And there we were a bit confused why we aren't handled to use try catch. Now when we use the CoroutineScope scoping function, suddenly we are actually able to handle the exception when we execute this app. So the CoroutineScope function rethrows uncaught exceptions of its child coroutine. And therefore, we can handle them with a try-catch on the call side. The main use case for the CoroutineScope scoping function is to use it in suspend functions in which we want to start new coroutines. And every time we call such a suspend function, we can be sure that we simply can use a try-catch on the call side in order to handle the exception. So this was the scoping function CoroutineScope. And now let's have a look at the scoping function supervisorScope, because this one is also quite interesting. Because with supervisorScope, we are able to create a new independent child scope in our job hierarchy. What do I mean by that? Well, let's have a look at another code example. And in this example, we again have a root scope in which we launch a new root coroutine. And in this root coroutine, we start another child coroutine, but we also open up a new supervisor scope. And in this supervisor scope, we launch two new coroutines. And as you can see in the hierarchy on the right, by opening up a supervisor scope, we actually installed a supervisor job in our job hierarchy. Now, what does this mean now? When you have a supervisor scope now, then this scope is really independent regarding exception handling. So whenever a coroutine in the supervisor scope fails, the exception is propagated up to the supervisor job, but not any further. So we have to really handle the exception in our supervisor scope. And we can do that, for example, by installing a CoroutineExceptionHandler. Before, however, I said that we are only able to install a CoroutineExceptionHandler in root coroutines. And here, they are really at the bottom of the job hierarchy, so that's weird. But actually, the crucial thing to understand is that coroutines that are started directly in the supervisor scope are now also root coroutines. And therefore, we are able to install a CoroutineExceptionHandler that is actually called. All right, so this was exception handling with coroutines. Now I want to simply recap all of my content. And if you are interested, I also created a cheat sheet of this recap, but more about this later. So to recap, the most important points for exception handling in Kotlin Coroutines is that exceptions can be handled directly in a coroutine with a try-catch block. And when we do it this way, then the coroutine does not complete exceptionally. The second important point is that when an exception is thrown in the coroutine but not handled by a try-catch, then the coroutine actually completes exceptionally. And when this happens, then the exception propagates up the job hierarchy. And it propagates up until it either reaches a root scope or a supervisor job. And while the exception is traveling up, every parent coroutine and also the sibling coroutines are cancelled. The next important point is that there is a difference between coroutines that were started, root coroutines that were started with launch and async, in the sense that the exceptions for launch coroutines are passed to the coroutine exception handler, but exceptions for coroutines that are started with async are encapsulated in its deferred object and are rethrown when we call await. Important point number 5 is that the scoping function CoroutineScope rethrows uncaught exceptions of its child coroutines, and therefore we can handle it with a try-catch. And the last important point is that you need to keep in mind two aspects when you use try-catch. And the first aspect is that when your coroutine is not completing exceptionally, then neither the parent nor the sibling coroutines won't be cancelled. And the second aspect is that suspend functions can throw a cancellation exception at any point, because a coroutine can be cancelled basically anytime. And if we catch all the cancellation exceptions, then the coroutine will continue to run. And in some cases, it then will waste device resources, but in more problematic situations, the app could even crash. So these were the 6 important points. As I said before, if you're interested, I created a coroutines exception handling cheat sheet that you can find on my website. You can see it is the first link here. And the second link here is a blog post where I also have a deep look into exception handling with Kotlin Coroutines. And the third link is actually a link to my GitHub project, which is called Kotlin Coroutine Use Cases on Android. And this project contains, I think, 17 or 18 of the most common use cases for using Kotlin Coroutines on Android. And of course, every use case has appropriate error handling in place. One last recommended resource is my online course about mastering Kotlin Coroutines for Android development, which also has a big section about exception handling, and you can also find that one on my website. All right, so that's it. Thank you again for participating in my talk, and I hope you learned a thing or two, and I want to wish you a nice conference. Thanks.
Да, спасибо, Лукас, за твой доклад.
Thank you, Lucas, for your reports.
Ты осветил несколько сложностей, которые
You have covered several difficulties that happen in the coroutines, but there are some new aspects that you haven't highlighted in Kotlin, or maybe specifically in coroutines, that we can encounter, that new developers can encounter.
Sorry, I couldn't hear the rest of your sentence.
Yeah, maybe there's some new aspects you haven't highlighted yet that new developers can encounter in Kotlin. Maybe related to coroutines or.
Sorry, the sound stopped to work. I didn't fully understand the question. Understood the question.
Вопрос.
Мой вопрос в следующем.
My question is the following. The new developers may encounter some difficulties on implementing Kotlin or coroutines in particular. Maybe there are some aspects that you haven't highlighted in your reports, that maybe some other aspects which are important to highlight.
Mm-hmm. You mean for coroutines? So yeah, coroutines are pretty, I mean, they look simple at first, but actually there are a lot of concepts that you have to understand in order to use them appropriately, because you have to learn new concepts like coroutineScopes, coroutine context, exception handling, coroutine jobs. So yeah, there are a lot of interesting new aspects when you learn about it, and some new concepts, and you really have to, well, check out the documentation. And I think also my GitHub project is a big help there, in which I implement the most common use cases for using coroutines on Android. So this, I think, can help a lot of developers. And yeah, it's a lot of new things to learn, but I think coroutines are the future and are the recommended solution actually from Google to write our asynchronous code on Android in the future.
Хорошо. Следующий вопрос.
All right. The next question.
Мнение входит в общество такое, что корутины, возможно, заменят RX.
There is
Что ты думаешь по этому поводу?
an opinion that the coroutines will substitute RX. What do you think about it?
I think the common opinion of most Android developers is that if you're happy with RX Java in your application, if you have a big application that uses RX Java, then it doesn't necessarily make sense to migrate to coroutines, because it's also a lot of work and also some risk involved. However, when you start a new application or implement new features in your existing application, then you should at least take a look at coroutines, because I think in the future, more and more developers will have knowledge about coroutines, but not about RX Java. Because if people are starting to learn about Android development nowadays, then they will most likely learn coroutines and not RX Java. So RX Java is a solid technology used in many big applications. However, the trend is that most of our asynchronous and concurrent code will be written in coroutines in the future.